Hello everyone. So today I will be solving a LeetCode hard problem, split array largest sum. Although it is tagged as hard, but it is not not so hard. So let's read the form statement. So we are given an integer array nums and an integer array k, integer k. Now we need to split this nums array into k non-empty subarrays such that the largest sum of any subarray is minimized. So what do we need to do? If we have a subarray, means if we have the array, we need to separate it into continuous segments of k, k segments, such that if we take the sum of each segment, then the largest sum that we will be getting is the minimum. That means we need to minimize the maximum here. Okay, and we need to return this minimized largest sum of the split. So obviously, this gives us a very big hint about what is the problem. The problem we need to solve is minimize the maximum. And for this, what algorithm will be using? Obviously, binary search. So that's why, just if you know, for minimizing the maximum or for maximizing the minimum, what algorithms we use, and if you already know this means binary search is used, so this will become a medium problem only, or to the easier side only. So let's see the test cases as well. So we have the test case as 7 to 5 10 8 and have the k as 2. So now we need to split it into two segments. So for example, if we split it into this segment, then left sum is 7 and right sum is 7 18 25. So here the answer means the maximum sum that we'll get is 25. Now another case will be 7 2 and then 5 10 8. So it will be 9 and this will be 15 8 23. So here the answer will be 23. Now if we split it from here, the left sum will be 9 5 14 and the right sum will be 18. So hence the sum answer in this case will be 18. Now if we split it here, it will be left sum will be 7 to 9 5 14 24 and right sum will be 8. So here it will be 24. So we see the out of all possibilities we need to minimize the largest sum. So the minimum that we get is 18, because 18 24 25 and 23. So out of these possible configurations, 18 is the minimum, and hence that will be the answer for this test case. Now let's see a different test case. 1 2 3 4 5. So here also k is 2. So now let's try for different splits. So if we try to do a split here, it will have 1 and 2 3 5 5 10 40. Okay, so here we will get 40. If we split it here, we will get 3 and 3 4 7 5 12. So here we will get the answer as 12. Now if we split it at 3, so we will get 6 and 9. So here we will get the answer as 9. And if we split it as 1 2 3 4 and then 5, so we will get what? 6 4 10 6 and 4 10, and this will be 5. So here we will be getting the answer as 10. So out of all these answers, since 9 is the minimum, hence that will be the output here. So as we already know, the problem is simply minimizing the maximum, and we simply need to apply binary search here. So now for applying binary search, what do we need? Initially means first we need to identify the search space on which we'll be applying the binary search. So obviously we need to minimize this maximum sum. Okay, so the search space will be the search space for search space for binary search will be the sum of elements, right? Now how much means the sum can go? So at minimum means now we need to decide the bounds of the binary search, right? The lows and the highs. So at minimum, the sum of any subarray will be the maximum element of the subarray, means the lowest bound that we'll get, since we need to minimize the largest sum of the split. So if this is the case, we have an array of multiple elements and we have the k as n, means k as n only, means we need to make n segments. Hence each segment will have a single element. And now the maximum sum that we'll be getting will be the maximum element of the array, maximum element. Okay. So in that case, the maximum element will be the answer. So hence the lowest bound that we will have will be the max element of array, and the highest bound will get when suppose k is equals to 1. In that case it will be the sum of the entire array sum. Okay, so in this case the high will be sum of elements of array. Okay, so these are the constraints for the low as well as high of the array. Now we need to identify how we will be minimizing the sum of, like, minimizing this maximum sum. So for that we need to, like, what, so we'll try to apply binary search. Okay, so we'll apply binary search till this condition is met. Now we'll find out the mid. So mid will be simply low plus suppose high minus low by 2. Why we do this? So that even if, like, since if these are in the ranges of integers, as you can see, since nums of I can go till 1e6, and 1e6 into 1e3 will be 1e9 only. Since these sums will remain in the range of integer only. But if we do like low plus high, 1e9, 1e9 plus 1e9, then maybe it will go to long. So hence, to avoid long values and integer overflow errors for integers, we simply do this, so that this simply represents what? Low plus high by 2 only. Okay, the same it represents. So we try to use this so that we avoid the integer overflow issues. Now we need to see whether it is possible to, whether the function means, I will be discussing the possible function. So if it is possible to make the largest sum, means largest sum of any split as mid, then what we'll do, we'll update our suppose answer as mid. And now we need to, since we need to minimize the maximum sum, so hence we'll be lowering the search space, right? So we'll be cutting off the right part, so that now we search for smaller range, means elements which lie on the smaller part of the search space, so that this value can be reduced only. So hence we'll update answer with mid, and we'll update high with, to move the range towards the lefter part. And else, if this is not possible, then that means there were, like, when we tried to do the splits, means the maximum sum that we are getting was greater than mid. Okay, so we need to minimize, means what do we need to do for each split that we'll be having. So for example, suppose these were the splits, we find out the sum. Okay, we found out the sum. Now each sum should be, means the largest should be mid only. Okay, so each sum should be less than or equals to mid. Now we try to make k segments out of it. Okay, now if we are not able to make k segments, that means, like, suppose k was 2, okay, and the elements were and the mid was suppose 3. Okay, now we need to make element sum 1, 2 and suppose 4. Okay, now we need to make k segments. So one segment will be this with sum less than or equals to mid, then one segment will be this with sum less than or equals to 3. Now we see, like, this is not possible, right? Obviously, since mid starts from max, so let's take it as, for example, 4. Okay, let's take it as 4. So one segment that we'll try to make is 3, 1. Okay, now another segment that we'll try to make is 2, 4. But as we can see, like, this has a sum 6, which violates the condition. Hence we'll never be able to make two segments which covers all the elements of the array, and the maximum sum of any segment is still lies less than or equals to mid. So in this case, this will not be possible. So if it is not possible, then what we'll do, we'll try for a higher sum, like from 4 we'll try for 5 or 6, right? So the range will move towards the right part only. Okay, so this is what we'll do. So in this case, what we'll do, we'll move low to the right part, and in the end we'll simply return answer. And now what do we need to find? We need to see how this possible function will be written. So what do we need to check? This possible function means possible of mid. What does it mean? It means, like, whether it is possible to make k segments, of sum less than equals to mid, means sum of each segment, sum of I. Suppose I is a segment, so for all I greater than equals to 1, less than equals to a. So these were the means k segments. So each segment should have a sum less than equals to mid, and all elements of array are covered. Means all elements are of the array are means a part of at least some segment. Okay, so hence all elements of the array should be included in these segments that we have. So this is what the possible function will be having. So now how do we check whether it is possible for a given mid? So we are given a mid. Now we need to check, suppose we are given the nums array. So we need to check whether it is possible to make k segments and still satisfy this condition. So what we'll do is we'll try to move from in the nums array, we'll try to move from the left and keep creating the segments of sum such that it is means definitely we'll need to cover the first element in as part of some segment, right? So if this first element is part of some segment, then we'll keep increasing the segment till our sum is less than equals to mid, right? Now as soon as this sum becomes greater than mid, then that means some element, means as soon as we encounter an element which made this sum greater than mid, we'll keep this element as the part of the second segment, so that our first segment has now concluded, and now this marks the start of a second segment. Okay, and keep doing the same till we cover the entire means entire array. And now in the end we need to see whether the count, means the number of segments that we made, it should be less than equals to k. Okay, why less than equals to k? Suppose if the number of segments made was greater than k, then that means we try to follow the best possible strategy to means divide the segments, but still we end up creating more than k segments, since it was not possible to get the mid, means it was not possible for this mid value. And why less than equals to k? Because if we are able to suppose 1, 2, 3 and k is suppose 3, okay, and mid is also 3. So now when we try to create segments, we'll see we'll create one segment of this and one segment of this. So we have created two segments, but k here was 3. So that means we can, if we are able to satisfy the condition with less than equals to k segments, then we'll definitely be able to satisfy it using k segments, because the sum will tend to decrease only. How? Because instead of 1, 2, which has sum 3, we'll make segments like this. Okay, so hence if we are able to satisfy this condition, number of segments that we'll making using this greedy approach, starting from the left and satisfying till the sum is less than equals to mid, and then changing the segment, and then simply counting the number of segments that we created, and in the end if this number of segments is less than equals to k, then it is true or false, else false. Greater than k, then it is not possible. We will simply check this condition, and I hope this condition is clear why less than equals to k, because if we are able to satisfy for less than k, then definitely for k will be able to satisfy the condition. Okay, so this will be the how the OK function will be looking. And yeah, this is the overall approach for this problem. As I said, it is on the easier side only, because we just need to see how we need to apply binary search here, and that was a simply hint given, we just need to minimize the largest sum, means we need to minimize the maximum. And yeah, so let's see the code as well for this approach. So what we'll do, we create these lows and highs. So low will be pointing to the maximum element of the array, and high will be the sum of all the elements of the array. So we'll be finding these lows and highs. Now at each step, what we'll do, low plus high by 2. We can also do low plus high minus low by 2. Okay, because here in the worst case it is going till 2e9, which will be long only, which will be integer only. Okay, so the means here it will not create any error, but if it were 1e9, the array values were 1e9, and then we had 1e5 elements. So in those cases we try to use this to avoid long integer overflows. Now we write the OK function, and if it is possible for this mid, then we update the answer as mid and reduce the range from this to the left side. Okay, and if it is not possible, then we reduce the range to the right side, and we simply return the answer. Now let's see the OK function. So OK function is the same. We try to create segments till the sum is greater than equals to mid, less than equals to mid. So we initialize sum with 0. Now initially we have this first segment created. We'll try to create this segment such that initially sum is 0. This means 0 is less than equals to mid. So we'll keep adding this keep adding elements to this segment, to this sum, such that it is less than equals to mid, and as soon as it becomes greater than mid, we'll start a new segment and increase this count value. So this is what we'll do. And if this is a simple check, we can avoid it as well. So if it is greater than mid, then it simply means like a single element is greater than mid. So it will simply not be possible to get the sum less than k, sum less than equals to mid for means any segment. Okay, for all the segments. So if at any point we encounter this, we can simply return false, or else if the sum plus it becomes greater than mid, that means this new element, which is it, is creating the sum to become greater. That means we need to make it as a part of a new segment. So if this becomes greater, then we'll simply make the sum to start from this value. So sum will become it of this new segment, and we will be increasing our segments count by 1. Means initially it was 1, then it will become 2. So we make the sum as it and increase the means count of segments that we have created. And else if is sum plus it is less than equals to mid, then it is good to add this it to our continuous segment. So we'll be adding it. So we'll simply add it. And now in the end, we'll check like whether the number of segments that we created was less than equals to k or not. And if it was, then it is means possible, else it is not. So this is what the approach was for this problem. And as you can see, like the constraint means the time complexity would be for this OK function, it would be big of n, and for this it will be what? We have the low will go up to 1e6 and high will go up to 1e9. So this such a space is from 1e6 to 1e9. So it is simply like log of 1e9 minus 1e6. Okay, so this is a means it will be of the order of like I think 1e9. So it will be to the power 30. So around 20 to 30. So it will work like 20 into 1e6. So this will be like working in this case. So now n is 1000 only. So 20 into 1e3, which will be like 1e5 only. So this will be like the overall complexity for this approach. And I hope like you were able to see how like just from the problem statement we are able to derive like this problem belongs to binary search, and when we later dig into it, we were like true like that it is a binary search problem. So let's try to submit the code as well and see like how well it performs, because the complexity is real less because of n being of 1000 length. As you can see, like it runs in 0 ms and beats 100% because of the low time complexity required. So this was the approach for this problem. And if you are not aware about this, so if we like need to solve similar problems of like minimizing the maximum or maximizing the minimum, then it is like mostly like in 90% of the cases it is sure that we need to apply binary search. And if you are able to write, the main part is writing this possible function. So if you are able to write this possible function in like optimal time, then in most of the cases the binary search solution works. So this was the approach for this problem. I hope like you were able to follow along. And if you have any doubts, feel free to comment down and I will be happy to respond. Thank you so much for watching.